I'm very happy to talk to this very broad audience who's interested in EFTs in general and different aspects of this way of thinking about physics. And I want to tell you about these couple papers and work in progress that appeared recently together with Cliff Chung here at Caltech and Andreas Helseth, my fellow postdoc, which I think might be in the audience, and also ongoing work, a few tidbits about ongoing work together with a student, Maria Derda and Cliff and Andreas. And the general topic is geometric self-theorem. So let me start just by explaining what self-theorems are and what is one of the motivations that one might have to think about this problem. So self-theorem is just the realization that the behavior of scattering amplitudes when the momentum of some particle is very small, it's universal. Okay, so we have some generic scattering process, some things coming up from infinity, going off to infinity. And then if we take one of the particles and we make its wavelength very, very large, then its momentum goes to zero. And then a particle with an amplitude with n+1 particles kind of factorizes into some sort of operator S acting on the amplitude for the hard process, which doesn't have that soft particle, that particle with very long wavelength. Okay, and so this is a very general idea, which is appears everywhere, and perhaps the earliest example of these self-theorems is the famous self-photon theorem by Lowe, Burnett, and Kroll, and also revisited by Weinberg, which is the idea if we take an amplitude of some process with some charged particles, and then also a few photons, and then we ask the question, what happens when we take the momentum of one of the photons to be very small? Then we can see that the result is universal. No matter what the structure of the hard scattering process is, the result takes the following form. The leading and subleading powers in the momentum of this soft particle. Then there's a singular term, which is the famous leading soft photon theorem, which just tells us that it's a sum over the external particles, and then there's a prefactor that only depends on the momentum of these particles. Q is the momentum of the soft particle, epsilon is the polarization of that soft photon, and then there's also a subleading soft photon theorem, which also depends on Q and the polarization, but then has some operator, in this case the angular momentum operator, acting on particle A inside of the hard process. Okay. But the form of this soft factor, this operator, is universal, and then we can apply it for any hard scattering process. Okay, so there's a similar self-theorem for soft gluons, which was discovered much later. So this goes back to the 50s. And just to give you a few more examples, another famous self-theorem is the so-called Adler zero, which is if we take an amplitude in chiral perturbation theory in the nonlinear sigma model, so it is an amplitude for scattering of pions, and we take the momentum of one of the pions to be very small, then the result is zero. And a simple way to think about this is that we only have amplitudes for an even number of pions, and then no matter what the subfactor would be, there's no amplitude that can appear on the right-hand side, so the only consistent answer is zero. And similarly, there's perhaps a bit more complicated self-graviton theorems, which again go back to Weinberg in the 60s. And okay, so the leading self-graviton theorem looks very similar to the self-photon theorem, except that now we have two polarizations. And then there's also a subleading and even a sub-subleading. So this is order q squared divided by q in the momentum of the subparticle. Okay, so in gravity, we have universality up to sub-subleading order. Okay, so these are a few examples of self-theorems in different systems, in gauge theories, in theories of scalars, and the study of such self-theorems has become quite an industry in the last decade or so. But one motivation to tell you the rest of my talk is the following. So there's two perspectives when people talk about these self-theorems, and two ways of thinking about them. So there's the rough idea that self-theorems are a consequence of symmetry. And we hear this all the time. It's a gauge symmetry of photons and gravitons that implies the self-theorems. For pions, for the Adler zero, we say that it's some non-linearly realized symmetry. So we are in a spontaneous broken theory of scalars, and then there's some symmetry which is nonlinear realized, and the way it shows up in the S matrix is in the form of a soft theorem. And then there's a different perspective, which is that, okay, soft theorems don't necessarily have anything to do with symmetry. They're just a consequence of the fact that we're asking questions about very long wavelength modes that and their behavior and their interactions with some hard scattering process should be universal just because of separation of scales, so just some general EFT ideas. Okay, and an example of this is kind of the coupling of ultrasoft modes at leading power in soft collinear effective theory. So we know what happens at leading power without needing to invoke symmetry at any state. Okay, so there's a third perspective which is related to asymptotic symmetries, which I won't discuss here. But you might ask, okay, which one of these perspectives is more fundamental? Which one is it? Is it that all soft theorems have to do with symmetry, or are soft theorems a more general thing that don't necessarily have to do with symmetry? And I will argue essentially via examples that soft theorems do not require symmetry in general, but instead just encode the physics of long wavelength modes, so of modes. They're a statement about effective field theory. They're not a statement about symmetry in general. Okay, so in order to argue this, we'll have to take a detour because the language in which I will illustrate this and the examples I will give are a bit unfamiliar. So we'll have to take a detour and talk about some geometric ideas, hence the title of this talk, which is Geometric Soft Theorems. But maybe first I will pause to see if there is any question about my motivation and what I just said.
I have a simple one, if I could just ask. So, I mean, it's kind of maybe a setup question, but some people might think that the way you've set it up and kind of like a juxtaposition of the idea of symmetry versus EFT is kind of like a little bit of a straw man, because the EFT will be defined by symmetry itself, right? So what ordering are you really putting in place here if it's really an EFT statement versus a symmetry statement when the EFT has to be defined by symmetry structure itself?
Well, the question is whether the soft theorem is a consequence of the symmetry of the EFT or not. So indeed, you organize operators in EFT and using symmetry principles, but can you have a soft theorem in a theory that has no symmetry? And the answer is yes.
Okay, so that's how that's the point you're making.
Yeah.
Okay, good. Thank you for the clarification.
Sure. Thanks for the question. Okay, so this is the outline for the rest of my talk. So I'm going to review and introduce some ideas about the geometry of quantum field theory, and I believe there's been other talks on the topic in previous instances of this series. And then I will introduce these geometric soft theorems, which are the key example that illustrates that you don't need symmetry to have a soft theorem. And also I will explain how these geometric ideas might provide a unified picture for all soft theorems that we know. So they all seem like different and they have slightly different structure, but there might be a way to think about all of them in a unified way. And if I have time, I will present an application of these ideas by deriving some on-shell recursion relations for generic massless scalar theories. So let's get started. So this is half of this will be a review, half of this will be kind of recent ideas by us and other friends. Okay, so when we think about scalars, so let's start with just with scalars. There's a useful way to think about theories of scalars. So a scalar field is just a map from space-time to some field space or target space manifold sigma. Okay, and then if we think about the Lagrangian for that theory, can be organized by derivative order. So we can have like a two-derivative term, which has some two-index object here, which is a generic function of the scalars. We have a potential, we can have some quartic term, et cetera, et cetera. Okay, and a useful way to think about these scalar fields, these maps are just some coordinates on this target space manifold. Okay, and from this perspective, a field redefinition where we take our fields, our scalar fields, and we just rewrite it in terms of a different set of fields, is just a change of coordinates in this manifold. Okay, so we have kind of different charts which have different labels, and then we can map every point in this manifold differently to our coordinates or to a choice of field basis. Okay, and so this is useful because many of the objects that appear in the Lagrangian actually transforms as some sort of tensors in this target space manifold. So for instance, the derivative of the scalar under this change of coordinates, just by using the chain rule, we learned that it transforms as a vector or as a one form. And indeed, many other couplings that appear here. So that in general, the Lagrangian is not invariant under Field-redefinitions, but the form of the Lagrangian will remain invariant if we choose to redefine these couplings accordingly. And an example of this is this kind of two-index object here. So this has to be symmetric just by Bose symmetry. Unitarity tells us that this needs to be positive definite. So what we learn, and also this transformation law tells us that this will transform as such, as a two-index tensor, and such an object is just a metric. Okay, so the two derivative Lagrangian just encodes a metric on this target space manifold. And similarly, many other couplings are tensors. Okay, so this is a familiar story to many people, and but let's think about the scattering amplitudes from this perspective. Okay, and some of these ideas go back to the 70s or the 80s. And okay, so when we think about scattering amplitudes of scalars, we need to think about the theory at some vacuum. And so we will expand the scalar field about a VF V, which is just some point in this field space manifold. Okay. And amplitudes do not depend on field bases. So this is a very general statement that follows from LSD reduction. There are several ways of proving it. It's sometimes called the equivalence theorem. So let's think about a field redefinition where we just redefine these fluctuations around the VF by shifting by some function. And then we can see that our action will change by a term proportional to the equation of motion, just by expanding in this small parameter epsilon. Okay, so this thing here at leading order will be proportional to p squared minus m squared, which is just the kind of the free equation of motion. And hence we see that scattering amplitudes won't depend on which field basis we choose. Okay, so the actual proof is more involved, but we can see that if we do a field redefinition, essentially we're just shuffling around terms which are proportional to the equation of motion. Okay, and these things, once you amputate using the usual LSD reduction, this will die. However, amplitudes depend on something else, which is a choice of frame. So if we ask about what is the overlap between our field variables and some one particle state that maybe also carries some flavor index, then the usual wave function normalization factor can be interpreted as essentially the specification of a basis on the tangent space of this field space manifold. Okay, so this is sometimes called a tetrad or a Firbein or something like that. So this is why we can use this to kind of diagonalize the kinetic term, et cetera, et cetera. Okay, so I told you that the amplitudes do not depend on field bases, and that means that they should be a function of some sort of geometric invariance on this field space manifold with these little indices, which are indices on the target space. Okay, so this will change if I change my basis in the target space, but they won't change if I do change of coordinates in my field space manifold. And examples of these geometric invariants are the curvature at the VEV, or covariant derivatives of the curvature at the VEV. And this was explained already by Volkov a long time ago. Okay, so this is some very basic and general ideas. Let's look at some examples to see how this works. So in a two-derivative theory where we don't have any potential, we don't have any other interactions apart from terms that look like this. So this is any power in the field, and then something that looks like the kinetic term. Then we can compute scattering amplitudes. And indeed, we find, after some work, that these amplitudes are a function of this geometric invariant. So for instance, the 4-point amplitude is just some linear combination of the curvatures times the familiar Mandelstam variables, which are just the sum over the momenta squared. Yeah, and similarly, at 5 points, we have covariant derivatives of this Riemann curvature tensor 6 points, we have more complicated things. We have contact terms that look like two covariant derivatives of Riemann and also curvature squared. And we also have factorization channels that correspond to kind of the gluing of these 4-point vertices that depend on Riemann squared. Okay. So this is the simplest example of an amplitude as a function of these geometric invariants or geometric covariant quantities, which are always evaluated at the point V or at the vacuum expectation value that of the field or kind of at the vacuum that we have chosen. Okay, and this form for the amplitude is valid for any two derivative theory. So you can choose your favorite theory, which has two derivatives, and you can compute the particular curvature tensors and their derivatives by organizing the Lagrangian in this way and just plug it in, and you will find the right answer. And an example of this, for instance, is the usual kind of nonlinear sigma model, kind of coset space sigma model. And this way of writing the amplitude slightly obscures the kind of the G mod H symmetry that you have, the symmetry of the coset. So in this case, for instance, the curvature would be kind of a contraction of the structure constants of the groups of the appearing in the coset or the Lie algebras associated with those groups. But okay, so this is what we give up, but we have manifest field redefinition invariants of the amplitudes, which is something that might be desirable. So this is a simple example. Let's look at another example. So if in addition to these two derivative terms, we add a quartic interaction. So this is a 4-derivative term of these scalars. Again, with any powers of this field, so this is a general function. Then we can compute the amplitudes, and indeed these are 4-derivative terms. So we find something proportional to this lambda tensor, and then their covariant derivatives. So you can go to higher points, then you will also have factorization channels, but this is the general structure. So all of these amplitudes are a function of kind of geometric quantities that are associated to these couplings, which are tensors. And this is always evaluated at the VEF that we decided to expand around. Okay, so let me mention that there's some related works that use many of these geometric ideas in different contexts. So there's very nice work by Alonso Jenkins and Manohar, which reintroduces this geometric language for amplitudes in the Higgs sector and describe the kind of general structure for like spontaneity broken theories of scalars. And there's also work by Cohen, Craig, Liu, and Sutherland, where they give kind of a geometric perspective on this question of like heft versus MEF, whether like electroweak symmetry is linearly realized or not somewhere in the Higgs moduli space. And they also discuss the massless or unitarity violation. And there's a series of papers by Michael and Andreas in the audience and their collaborators thinking about a geometric reformulation of the standard model effective theory and different aspects of it, which has been very successful. And even a recent work about geometry of derivative field definitions by, again, Cohen, Craig, Liu, and Sutherland, which I'll touch on a little bit next. Okay, and I believe there have been previous talks, at least by 2 people in this list, on some of these aspects. Okay, so but today we won't be talking about this geometric the geometric ideas as applied to these points. We'll talk about something else. So some questions that you might have at this stage is, okay, so you talk about these changes of coordinates, but what about more general field definitions, things that also depend on derivatives of the field? What about non-tensorial coupling? So if we have 2 derivatives on this guy, then this doesn't transform as a tensor anymore. Okay, sorry, there's a typo here. There should be 2 terms like this. But now there's also a term that transforms kind of finally with some quadratic terms in the derivatives of the field. So this is not a tensor anymore. So what do we do about this? What about spin? What if we have gluons or gravitons, other bosons? Can we also think about them geometrically? And what else is this geometric picture good for? And I'll try to address some of this. And So the first one, it can be easily addressed by generalizing a little bit the idea of expanding around some web. So instead of expanding our theory around some constant web, more generally, we can just think about expanding around some background field. Okay, so some solution to the equation of motion, which I called here phi bar. And then the analog of taking derivatives with respect to the web would just be to take functional derivatives with respect to this background field. Okay, and many of these geometric ideas actually naturally generalize in the presence of this background field. So now my metric, for instance, doesn't only depend on the web, it depends on this full background field, okay, and on the momenta of the particles in general, and also on the momentum of the background field. Okay, and then if we want to take derivatives of the metric, then now we have to replace this with kind of covariant functional derivatives of this metric with respect to background field. So this will be in general a function of the particles that appear in the Lagrangian and the momentum of the background, and then some function of the background field, which I'm not writing here. So this is very useful because it gives us a unified picture for any interaction, just by thinking of it as a two-derivative theory with some dependence on the background. Okay, so I can repackage any theory of scalars in the following way. So this is just, again, some sort of metric that now depends on some field and its derivatives. And then I pick out two of these guys, and then, okay, so here I wrote it in momentum space, so these are the derivatives acting on this. So this has the exact same form as the two-derivative theory I wrote, except that now the general kind of nth derivative of the metric will just be something like 1 over P1, P2 times the endpoint Feynman vertex. Okay, so this is a very generic way of thinking about the Lagrangian, and indeed, just by how one builds geometric invariants out of a metric, then all the geometric quantities that you might define using this metric by taking covariant derivatives, by taking functional derivatives, they will be invariant under Field-redefinitions or covariant under Field-redefinitions, even off-shell. Okay, so there's a set of geometric invariant quantities or geometric covariant quantities that we can construct just by organizing an arbitrary scalar Lagrangian in this way, and then taking functional derivatives of this object. Okay, so an example is one can build a off-shell Riemann tensor that depends on the momenta of the particles, which is fully covariant off-shell. Okay, so let's see some examples of this in some simple theories. So for a two-derivative theory, as the one that I showed you earlier, this just reproduces the usual invariants that were just a function of the web. Okay, so there, the background field is not really necessary because we don't have any derivatives on this field phi. So we just reproduce the usual story. So this gets a bit more interesting for a theory where we have potential interactions. So now this metric that I wrote before had a 1 over P1.P2, so it's a non-local object. And indeed, the corresponding Riemann tensor will be some non-local function of the momenta of the particles. So at the 4-point level, it's just something that looks like this. So these are T and U, the usual Mandelstam variables. B3 is just the 3-point interaction. B4 is the 4-point interaction in the potential. And then there's again some function of the background field that I'm not showing here, but that it's crucial to make this whole thing Field-redefinition covariant off-shell. Okay. And another example, well, first of all, you can check that this has the usual symmetries of the Riemann tensor. So if I swap particle 1 and 2, then T and U get exchanged, so this is antisymmetric. If I swap P1, P2 with P3 and P4, then T and U remain invariant, and this is symmetric. Okay, another example is if we have a Dirac-Born infill theory. So this is kind of the theory of the Goldstone modes of spontaneously broken Lorentz and translation symmetry by the presence of a brane. Then this is just T minus U times kind of the 4-point interaction. And from now on, I'll be omitting this function of background fields. And similarly, there's these theories, maybe you've heard about them, special Galilean, there's special EFTs that have very good soft behavior. And for the generic class of these theories, for which the amplitudes die as some power of the momentum, then the Riemann tensor looks like just power of t minus power of u. Okay, and you can check that this, as I said, has the symmetries. All of these have the symmetries of the Riemann tensor. They satisfy Bianchi identities, et cetera, et cetera. Okay. Another thing that you can check is that it also satisfies the second Bianchi identity. So if you take further derivatives of the Riemann tensor, then you can check that all the usual geometric identities are satisfied by these objects. Okay, so this is not only a curiosity, we can actually use this to compute scattering amplitudes. So just take your favorite amplitude that I wrote before for the two-derivative theory and insert these curvatures. And indeed, if you insert a curvature in the previous slide, in this formula here, for the theory with a potential interaction, you reproduce the usual 4-point amplitude where we just have 3 factorization channels, essentially by the phi cubed interaction, and then the contact term from the phi to the 4th interaction. And similarly for Dirac-Von-Infeld, you can plug it in and you will find the usual answer, which is s squared plus t squared plus u squared. Okay, so this is just to motivate that this geometric way of thinking gives a kind of a unified picture of scattering amplitudes for massless particles, or at least for massless scalars so far. And this manifests field-redefinition invariants at the expense of locality. So for instance, here we don't see any of the factorization poles in the amplitude with a cubic interaction. So these are hidden inside of the curvatures. And also a point that I'd like to make is that the fact that we can write the amplitude as a function of these geometric invariants, crucially, this is only true on shell. But as I said, these geometric quantities are field-redefinition invariant off shell. Okay, so we couldn't write the amplitude in terms of these curvatures if we were not using on-shell conditions at some stage. But once we've done that, then the objects that show up here are actually covariant off-shell. What about spin? Everything I said essentially holds when we have spin. Again, it's the same organization of the Lagrangian. We can think of everything as a two-derivative theory with some complicated metric. Now the metric will depend on the color and the Lorentz indices of the gauge fields, and again will depend on some background field. And for ordinary Yang-Mills theory, this is very simple. Kind of the first derivative of the metric is just the cubic vertex. The second derivative of the metric is just the 4-point vertex, again divided by P1, P2. And the geometric expansion still works. So you can plug this in again into this formula, and which is manifestly field-redefinition covariant. And in this case, we obscure locality and gauge invariance, but we get the right amplitudes. Okay, so this is very nice. So there's some geometric way of thinking about scattering amplitudes, and this is only one of the many applications of this geometric perspective. And now I'm ready to introduce so-called the geometric subtheorem that we found that uses this geometric language. And this will be the main example of a subtheorem that doesn't require any symmetry. Okay, so the intuition is the following. The intuition is that, or more than the intuition, is that the general structure of the subtheorem is that if we take an amplitude with a massless scalar, and then we take the self-limit of that massless scalar, then the result should be something like this. So there should be a part which is just a derivative with respect to the VEF of that scalar. And if that scalar lives in some target space with some geometry, it should be a covariant derivative. And this derivative just tells me essentially how every vertex changes when I take some soft particle, some soft massless scalar. This should be just like a shift of the VEF. Okay, so this is a very, very long wavelength, and in the limit, it just becomes a constant. So this is exactly like shifting the VEF. And this derivative, when it acts on vertices, it just kind of precisely takes some derivative. So this is like a shift of the VEF, and then for a propagator, it will also pull some 3-point vertex. Okay. However, we have to correct this by something, and this is essentially the insertion of an external 3-point vertex. Okay, so there's some singular term in a soft limit that can appear when we have particles with mass, and this appears as kind of this singular piece from having a soft emission of an external leg at 3 points. And this just encodes the idea that, okay, when we shift the VEF of the scalar, the mass of some particle can shift. Okay, And precisely the variation of that propagator is given by the 3-point function with an extra propagator. And this is the fact that the on-shell condition is changing as I move my BEV around. Okay, so I need to make sure that this operation makes sense, as I will describe in a second. Okay. So this is the general structure. You can put in all the indices and figure out all the details, and then the soft theorem looks like this. So we have a bunch of flavor indices. So the covariant derivative is along the direction of this massless scalar. And then the thing that I wrote as the covariant derivative of the mass is just the 3-point vertex, which one can think of as kind of the derivative of the mass matrix. Okay, and then this piece here, which is a singular piece, will be the leading soft, and then this and this will be the subleading soft because they have an extra power of q. So this will go like 1 over q. This will go as q to the 0, and this too. Okay, so this soft theorem doesn't require any symmetry whatsoever. And instead, this is a precise encoding of this intuition that I already mentioned, which is that the soft scalar should be just a shift of the VEF. So this is just saying if you have a very long wavelength mode, then I can just think of this as a constant field, and then see how this would affect my scattering amplitude. Okay, and this soft theorem. So yeah, if we start with an amplitude at some VEF v, and we take the soft limit, this is exploring a neighborhood in the field space of that point. So it's telling me what the amplitude looks like in the neighboring theory, which lives at a slightly different vacuum. And this is valid for any massless scalar in any theory of scalars. Okay, so this you can add terms to your metric to break all symmetries, and then this soft theorem will still be true. Okay, I will say in a second what's special about theories with symmetry, but this is completely general. And also let me comment that we have a non-perturbative proof for this in the massless theory, which is very similar to Adler's proof of the Adler zero. And then for a theory with massive particles, we have this soft theorem is valid at true level. And it's different from other soft theorems because in order to use it, we need to be able to take derivatives of the amplitude. So we need to know the amplitude as a function of the VEF. And that's slightly different from other soft theorems. Okay, so this is a technical comment, but it's something conceptually important. So I'm telling you that I'm taking derivatives of the amplitude with respect to a VEF, but this is not an on-shell operation. If I take the on-shell condition, and if I take a derivative with respect to a background field, or sorry, with respect to a VEF, then generically the mass will depend of some particle will depend on that VEF, and hence this doesn't give me 0. So this should be 0, but then when I take a derivative, it's not 0. And this is why we have this second term in our soft theorem. Why the soft theorem is not just take a derivative with respect to the VEF, which encodes a shift, but we have this extra term that comes from the 3-point function. And a way to think about this is like an on-shell connection. This is something that takes objects which are 0 on-shell to objects that are 0 on-shell. So this thing here, this precisely pinches this on-shell condition and then cancels this minus m squared here. Okay, such that this geometric solve theorem is well-defined for amplitudes. For each individual term is not well-defined, but the combination of the terms is well-defined. Okay, so let's look at some examples. I showed you before some amplitudes for this two-derivative theory. So now let me take particle 5 to be soft. And if I just cross every single Mandelstam invariant that depends on particle 5, indeed I recover the covariant derivative of the 4-point amplitude, which I also showed you. And similarly for a quartic theory, so the 4-point amplitude looks like this. And then again, if we take particle 5 to be soft, then we remove every Mandelstam, which depends on particle 5, and what remains is just the covariant derivative along the direction 5 of our 4-point amplitude. Okay, so these are very simple examples for amplitudes that only depend on contact terms, but you can include factorization channels. Then the fact that this soft theorem works is much more non-trivial, but it still works. Okay, what about double soft theorem? So instead of taking one particle soft, we can take multiple particles soft. And there's different ways of doing this. There's a consecutive way. First, we take particle A soft, then B, and vice versa. And this simply gives, in a theory of massless particles, this gives a commutator of these covariant derivatives, which is nothing else than the curvature. And this is the way we can measure the curvature of the field space, by taking consecutive self-limits. And similarly, if we take the simultaneous double soft limit, where we take two particles soft at the same time, then there's two terms. So this is what you would have expected just by doing a Taylor expansion. But there's also a term that sees the curvature of the field space. And the difference between the two is that this double soft limit encodes different paths in field space if we do it consecutively or simultaneously. So the consecutive double soft limit is like going from vacuum V to vacuum V prime by tracing a little square, like in two different directions. First particle A goes soft, then B, or B and then A. And then the simultaneous double soft is just take some path in field space, which is specified by momenta here. So these are just some angles that tells me how to go from V to V prime. Okay, so this is very nice, because when we explore multiple soft limits, we start to see the curvature of the field space. Okay, so a few comments. So I told you that kind of this geometric perspective gives us a way of encoding both leading and subleading soft theorems for massless scalars. And this challenges this common law that soft scalar theorems are associated to nonlinear realized symmetries. Okay. So as I told you, I don't need any symmetry at all to have this geometric soft theorem. And instead, the soft theorem just tells me how I move around the space of vacua of my theory, or around different theories which are related by some shift of the vector. And this kind of a generalization of soft theorems for Goldstone bosons, which are associated to symmetry. And I will explain this in a second. And what's special about theories with symmetry is that neighboring vacua are actually exactly the same theory, but this is not necessary for having a soft theorem. Okay, so let me elaborate on that point. So what is special about theories with symmetry? Okay, we want to understand, why do we usually talk about soft theorems only when we have symmetry? So for this, let's think about these theories of scalars, and let's think about symmetry in this context. So when we think about symmetry, we just think about shifting my field phi by some function of the field, typically. So this is some infinitesimal transformations, and the way of thinking about this is, from the geometric perspective, is just saying I'm doing an infinitesimal diffeomorphism, which is encoded by some vector field K. And all the couplings in my Lagrangian will shift according to the usual transformation laws of tensors. So when we do a diff, an infinitesimal diff, a tensor shifts by the lead derivative with respect to that vector. Okay, and the fact that we want our theory to be invariant means that this should be 0, and this is the well-known Killing equation. The fact that we have an isometry of our field space manifold. Okay, so this is a famous example, like just rotations on a sphere are an isometry, and this is encoded by the vector field depicted here. Okay, so from this perspective, one can write the Ward identity in a nice way, in a nice geometric way, which is just saying that the lead derivative of the amplitude with respect to that vector field evaluated at the bev is 0. And this is what's special about theories with symmetry. So we have a Ward identity that actually relates derivatives of the amplitude with respect to the bev to something that doesn't require taking a derivative of the amplitude. So here we have the covariant derivative of this Killing vector K times the amplitude. And here we just have the derivative of the amplitude. So if we apply this to our geometric soft theorem that just told us that this self-limit of a particle is the derivative of the amplitude, in a theory with symmetry, what we learn is that that self-limit instead is multiplicative. We don't really need to take derivatives of the amplitude with respect to the bev, because the answer of that derivative is dictated by symmetry. It's just changing this Killing vector. Okay, so the only difference between theory at V and V plus delta is that my Killing vector has shifted a little bit. Okay, so this is a general statement. So what we'll find is that for theories with symmetry, we don't need to take derivatives with respect to the bev in a soft theory. So let's look at an example. So this is an example which is perhaps unfamiliar. So this is soft theorem for non-symmetric space Namu-Goldstone bosons. So we're used to thinking about Goldstone bosons for some pattern of symmetry breaking. G goes to H. H is a linear symmetry in the vacuum, and few generators of G are spontaneously broken. So here in this language, we have a bunch of killing vectors. The ones that I denote by T, they're the generators of H, which are linearly realized. These X's are the broken generators, which are non-linearly realized, but they're in some representation of H. Okay, so this commutation relation tells me that this transforms in some representation of H. But in general, the commutator of two broken generators can be a linear combination of broken and unbroken generators. And the general soft theorem, what we learn is that the soft limit of a particle, of a massless Goldstone in this case, is just proportional to this structure constant that appears in these commutation relations. The structure constant that relates broken generators to broken generators. Okay, and one can check that this is just the covariant derivative of the broken generator. Okay, so this is a general soft theorem for Goldstone bosons. And a special instance of this is the well-known Adler zero. So what's special about the Adler zero? Adler zero is that we have a symmetric coset. Symmetric coset is a coset that has an additional Z2 symmetry, some G parity that tells us that, that if we flip the sign of the broken generators, they should be a symmetry. And this, of course, kills these structure constants here, and we have a zero on the right-hand side. Okay. So this gives us kind of the geometric perspective on soft theorems for ordinary Goldstone bosons of spontaneously broken global symmetries, both the kind of more unfamiliar non-symmetric coset and the more familiar symmetric coset, which is just the Adler zero. Okay, let me give you another example. So this is a self-dilaton theorem. So the self-dilaton theorem is a theorem for spontaneous breaking of some space-time symmetry, scale invariants, also conformal invariants. That are leading order, only scale invariance matters. And the geometric way of deriving this is to realize that actually a dilaton, scale invariance implies that the dilaton is a compensator for every scale in our Lagrangian. And this means that actually it's a flat direction in field space. So there's no curvature in the dilaton direction. And this means that all covariant derivatives are just partial derivatives with respect to the VEF. Okay, so you can think of this as some cone where there's some complicated geometry, but the dilaton direction is always some flat direction. Okay, so the self theorem would just tell me that the limit of some amplitude is a derivative with respect to the VEF of the dilaton, if I take a self dilaton. But by dimensional analysis, this is just given by dimensional analysis. So derivative with respect to the VEF. So this is the K constant, which tells us what the dimension of the dilaton is. This is just the usual dilatation operator acting on momenta, and this is the dimension of the amplitude. And indeed, we learned that the derivative with respect to the VEF of the dilaton is this thing on the right-hand side, which is a familiar self-dilaton theorem. Okay, but note that this is a much easier way to think about it, which is just a self-dilaton. We just take a derivative with respect to the VEF of the dilaton. And this also works if you add some massive particles to the mix, as we explained in the paper. Okay, so we see that this geometric self-theorem kind of gives us special instances self-theorems for Goldstone bosons of both spontaneously broken internal symmetries, internal global symmetries, and space-time symmetries. And this means that indeed, as I said at the beginning, we don't have symmetry if and only if we have a self-theorem. In general, what we have is that if there's symmetry, the self-theorem is multiplicative. Okay, so the self-theorem is an operator that acts on the amplitude that doesn't involve taking derivatives with respect to the VEF. That is just some operation, some multiplicative factor, or at most some operation on the momenta of the amplitude that doesn't require knowing at which vacuum we are. Okay, so the latter perspective that self-theorems are just some consequence of kind of effective field theory thinking and not of symmetry. These are some examples, these geometric self-theorems, and explain what's special about symmetry. Okay, any questions about that? All right. Okay, so there's a raised hand. Please go ahead.
So maybe Alberto, go ahead first.
Yeah. Hi. Can you hear me?
Yeah.
Yeah. Okay. So yeah, I find all this very interesting. Just one question. Maybe you mentioned it, but I missed it. So for there to be a soft limit on shell at all, you need these particles to be massless.
That's right.
And that's usually guaranteed by a symmetry. So in a sense, there is an implicit symmetry statement when you take a soft limit. No?
You're saying if I shift the web, maybe my massless particle will become massive?
Yeah,
so
in general, I'm saying...
So it's important that we are expanding around a true vacuum of the theory.
Yeah.
So we don't have a tadpole. So if you had a tadpole, then your massless particle could become massive at when you shift the order at linear, when you shift the web at linear order. But if you're expanding around a true vacuum, at the linear order, the massless particle remains massless.
I'm even saying before even taking any derivatives with respect to the web, the existence of a massless particle is usually guaranteed by a symmetry. So that's the case for Goldstone bosons. It's in a sense the case also for photons and gravitons. Even though we say, okay, gauge symmetry is not real symmetry.
Yeah, I mean that's indeed one way of thinking about it. But for instance, I can have a manifold that doesn't have any symmetry whatsoever, and still have this soft theorem, right? So you're saying, you can have, so that is protected by a symmetry, and indeed, if you compute loop corrections, then you might worry that you will generate a mass or something like that. But so I agree with those statements. But here it's crucial that we're working in a neighborhood of a vacuum where we have a massless particle, and then that particle remains massless in that neighborhood, and then the soft theorem is a more general statement.
Okay, thank you.
Okay, thanks a lot for the question.
Oh, looks like no other questions. I guess time to move on.
Okay, so let me explain that maybe this is a more general way of thinking about soft theorems. So we can generalize this intuition and just think that can ask the following question: can we ask about the general soft theorem in the same way? So we have that the soft limit of some amplitude will have two pieces. One will be just a derivative with respect to some background field, which represents this soft particle. And then to remain on shell, we'll have to have some additional piece, which is just a 3-point vertex. So this is what I call the on shell connection. This is the thing that makes sure that we're remaining on shell, that taking these derivatives is a well-defined operation on scattering amplitudes. Okay, so there's a in this paper that appeared recently, they also think about this 3-point function as a Christoffel symbol or as a connection. So it would be interesting to understand the precise relation between these two perspectives. But let's just see if this perspective works. And indeed, it works in many examples. So for instance, we can think about the leading coupling of scalars to fermions. So this is some term that has a single derivative on the scalar, and then it's some fermion bilinear like this. Okay, and here the soft theorem works. So if we take the soft theorem here, it's just a modified covariant derivative that has an additional piece that depends on this. And this is just a pinch of this 3-point function because we have a derivative here. So indeed here the soft theorem works, and it just tells us that if we have fermions in the fermionic directions, we have some torsion in our connection. Okay, so an example of this is a simple example is some dipole coupling. So we can couple a scalar to a fermion bilinear, some gauge field. And if we look at the 3-point amplitude of 2 fermions and 1 gauge field, it's something like this in 4 dimensions. The 4-point amplitude indeed is this modified covariant derivative with torsion of this guy. We can keep going 5 points. It also works, and the soft theorem works. Okay, and if you think about the couplings of scalars to the Goldstone to the gauge fields, then one finds kind of an on-shell version or kind of a soft version of the Goldstone boson equivalence theorem. So instead of asking about scattering of very high energy longitudinal W bosons, we can think about kind of a soft scalar probing the scattering of W bosons. So instead of, so it's essentially the same limit, and we see that Goldstone boson equivalence theorem shows up as some sort of soft theorem. So I won't elaborate on that, but you can ask me more at the end. What about the soft photon theorem that I started with? So I told you that the oldest soft theorem is this low Burnett-Kroll. And indeed, here everything works. So if we look at kind of the metric that relates scalars and photons, it's just essentially this vertex here. And so this connection here is given indeed by the 3-point vertex of the theory. And then the covariant derivative is just a derivative with respect to the background. And again, as a consequence of symmetry, the fact that the background always appears in conjunction with a derivative, this derivative with respect to the background can be traded by derivative with respect to momenta. And this is a consequence of gauge symmetry. And indeed, when we combine these two terms, we find the leading and subleading soft photon theorems now reinterpreted as this geometric statement about how things shift under some transformation of some background field. And similar ways of thinking about soft gluons and gravitons are work in process, and they're just a bit more complicated because of the non-abelian nature of the interactions in that case. Okay, so that's kind of some food for thought, and this is the work in progress. Can we think about all soft theorems from this geometric perspective? But now let me finish with something else, which is an application of these soft theorems in the context of on-shell recursion relations. So we want to use these geometric ideas to compute amplitudes in some efficient way. And the most famous example of on-shell recursion are like things like VCFW or all-line shifts. So just to review how this works, so we take a scattering amplitude, we deform its momenta by some complex parameter z and some vectors here, making sure that on-shell conditions and momentum conservation, these things are respected. And we write the following contour integral. So we write an integral which is a residue around z equals 0 of the deformed amplitude. So that residue just gives you back the amplitude. But then if we blow up the contour by Cauchy's theorem, this equals the residues at everywhere else in the complex plane, and these residues are given by factorization channels. So the only poles in the amplitude come from places where a momentum becomes on-shell, which can happen somewhere along this z-plane, and the residue is just given by a product of lower point amplitudes. Okay, and if this arc at infinity can be dropped, so if there is no pole at infinity in this dispersive integral, then this gives us a way to do on-shell recursion. Okay, so to build higher point amplitudes from lower point amplitudes without reference to some Lagrangian or anything like that. We just start with some seed amplitude, say 3 points, 4 points, and we can build all higher point amplitudes. Okay, so probably everyone has heard about this. Maybe a less familiar example of this is the so-called soft recursion. So there's many of these theories that have nice soft limits or enhanced soft limits, in particular things like Adler 0 and its cousins. And these effective field theories are theories of derivative coupled particles, things with many derivatives. So generically they have a pole at infinity. They grow very fast as z goes to infinity. But this can be ameliorated by some subtraction. So we just divide by some factor that depends on powers on z, so that we don't actually have a pole at z equals infinity. So this factor looks something like this, where the points where z equals 1 over c, so the poles introduced by this thing are designed such that that's where a particle becomes soft. Okay, so and for the case where you have an Adler 0, there's no residue associated with those poles because the amplitude is just 0 there. And indeed, this enables on-shell recursion. So again, the remaining residues. So here we have some residues which naively they're given by the soft limits, but those vanish, and then the only remaining ones are the usual factorization channels, and they give something like this, that the amplitude can be written as a product of lower point amplitudes. Okay, and so just running the same argument, we find that there's kind of a geometric soft recursion which is valid for all massless theories where the self-theorem is very simple like this, and the same argument applies, but now we do have a residue on those extra poles that we introduced to improve the behavior at infinity. Okay, so in addition to the factorization channels, we have the residues in the self-limits, and these are just given by our geometric self-theorem. Okay. Now, what's the way to think about this? The way to think about this is that the city of the recursion, in this case, will be the 4-point amplitude at every VEF. So we need to know the amplitude everywhere on the field space in order to be able to use this recursion. And this is because we're going to be taking derivatives of the amplitude. So to go to endpoints, we need to know the nth derivative of the amplitude at 4 points. And this means essentially knowing its Taylor expansion up to order nth. And if we want to know all amplitudes, we need to know the amplitude as a function of the VEF. Okay, and these recursion relations are valid for any theory of massless scalars. Okay, so this always works, as opposed to kind of these self-theorems for special effective theories that have nonlinear realized symmetries or things like BCFW that are true for gauge theories or theories of gravity. Okay, so I think I'm almost out of time, and so let me conclude here. So I explained that the geometry of field space is a useful principle that can be extended beyond simple changes of coordinates to kind of general field definitions, and that can be used to organize bosonic amplitudes in a geometric way that exposes their field definition invariants. And in addition, this kind of geometric way of thinking gave us a new geometric self-theorem that tells us how amplitudes change when you shift around field space. And more generally, it reveals kind of a general organizing principle for leading and subleading self-theorems, which we're working the details of right now. And kind of challenges some of these usual notions that relate self-theorems to symmetry. Okay, so there's many questions that remain, at least a couple of them. Can we derive kind of a general double soft limits for any theory using this geometric perspective? Can we also derive general recursion relations using this? What about sub-subleading self-theorems? That's something that I haven't touched on. What about soft fermions? I've only talked about soft massless scalars and maybe photons, in general bosons. So we know that there exist soft fermion theorems when we have a spontaneously broken symmetry. So there's a famous Goldstone theorem for spontaneously broken supersymmetry. But there's a question of whether there exist more general soft fermion theorems if one thinks along the lines of what I talked about today. And also, what about Goldstones that appear in non-relativistic systems or systems where you spontaneously break combination of global and like internal and space-time symmetry? And perhaps a more interesting question for applications is, can we use these self-theorems to move a finite distance in field space? Okay, so naively one runs into this Zeno's paradox, which is that if we take a particle soft, then the next particle that I take soft, it needs to be softer. So every step that we take will be kind of half of the size of the previous step, and we won't be able to go very far. But more generally, there's the intuition that by thinking about kind of many soft particles, we could explore kind of long distance in field space, and these would be interesting, for instance, in the context of the Higgs effective theories. And it's related to ideas that have appeared already in some of these papers that I mentioned. Okay, so with that, I think I will finish here, and thanks everyone for listening.